And back, yes.
That's the important part of the paper, the and back part. Well, thank you for having me and for being here. It's the first time we meet these fellows since quite a while ago. And as you can see in my face, I totally underestimated the sun yesterday. See more of it the rest of the day. Now this is a project that I started with Manuel Förster, who's assistant professor in Bielefeld at the Center for Mathematical Economics a couple of years ago, and then we had a first working paper, and this working paper you can actually find online, I'll show you a little bit later. But we were not that happy with the paper for reasons I will show you later. So we basically started from scratch with the same idea and developed it further, and this is what you see here. We have a model and we have some data and we bring that together and we have, I personally have nice, surprising results here in terms of how you can explain certain data from New York, from the New York Police Department, and how they target people in the street for random searches. So this is what that is. I said to you, we started a while back. Basically, we started in late 2020, early 21, when George Floyd was killed. So here you see some pictures of people who died from police violence in the US, in Germany, in France. This kind of motivated us to start with the project, but we are not talking about police violence here, so this might be a bit misleading. What we're actually talking about is why are black people targeted more often by police when it was random searches. If you look into data from 2012 in New York City, what you will find is that random searches in the street targeted black people to 58%. There was a policy, it's called stop and frisk. If a police person sees somebody in the street who acts suspiciously, whatever that means, it's a very, very little term here, they can stop them and frisk them. And 58% of all searches were conducted with black people. Even though black population in 2012 accounts only for 22%. So there's a huge bias here. So this is why is the important part, right? So there is a bias here, the question is where does it come from?
Any other group who's being discriminated?
For Hispanics, you see it's slightly less. For white people, 33% of the population, but only 7% of all searches. And for others, including Asians, 60% of the population, 9% searches. So it's really the black population that is targeted. For Hispanics, it's more or less representative, although it varies from year to year. But I will show you more data on that later from 2003 to 2020.
That's quite convincing, but you do not control for neighborhood.
No, I do not. We are not there yet. So what we have from the New York Police Department are huge data sets that basically list every single search that has been conducted. So
including the neighborhood?
Including the neighborhood, yes. So we will probably do that eventually, but I want to focus on the theoretical part. I'm a theorist, I'm not a data person. We just used these data to basically illustrate our point, and then we were surprised by how well we could actually do that, which is why then we started rethinking, should we not do more with these data? But let's do the theory first, and then we will have a closer look into that. Now, what's a theoretical idea then? Somebody decides that he wants to target, or that they want to target black people. Well, how do we make a decision? Well, we are all economists. A decision is a solution to some problem, to some optimization problem. It might not be a good problem, but usually it is a problem, and this problem depends on a belief. We do not know who is criminal and who is not, but we will have a belief about that, and this belief will influence the research. So far, so easy. This is the racial profiling part. Now, where does the belief come from? Well, the belief usually comes from what we observe. We would hope so. But what do we observe? And this is the critical part. What we should observe is every single search and result. But what we will pay more attention to is what we actually find. Right? So we see all these criminals that we have identified during our searches, and we will see most of them are actually black. And we will totally forget that this might be because we've mainly targeted black people. That's the twist. So we have a bias sampling set which causes a biased belief, which causes a weird decision in our problem, but this solution then leads back to a bias sampling set. So what we want to do is basically find an equilibrium that explains that. And we want to develop a belief that comes from the bias sampling set and explains the solution that we observe. And the solution we observe itself should give you exactly the belief that we start with. And so an equilibrium consists of a belief and search probabilities for the different groups. That's the principal idea. Alright.
Is it correct that if you're over-targeting a population, so it balances your suspicion because you take people that are less and less really suspicious, and it makes this population, in percentage, the guilty people among this that you searched in them is less, right? So it has an effect of balancing your suspicion.
Yes, exactly. So there should be an effect on what we call marginal productivity of search. The more I search, the marginal productivity or the marginal probability that I actually find somebody who has behaved criminally should decrease. This is precisely what was missing in our first paper. There we said, if we search, it's purely random, it doesn't matter how many people you have searched. In this model, we basically assume that there is a decreasing marginal return. And of course, if you then solve this optimization problem, this will give you the first order conditions. They should somehow balance, and this should somehow describe who you should target.
In reality, there is also a price for false accusation.
Yes, also part of the model.
Vary between the left and right.
Yes, that's true. That's true. So this is something we do not include here. So there are two things we are not doing. We are not working with a taste for racism. So we are not making any assumption here that people just like to target black people because whatever is that. And we do not assume that there is any difference in punishment for targeting wrong people. What we do assume is that there is some kind of cost for having an unbalanced set. So if you over-target one group, this will negatively affect your utility. And this will be parameterized when we go back to it. Okay. Now, once we have this equilibrium, we can tell some things that will happen if, for instance, we would start defunding the police. What does it mean? Of course, we will target fewer people, but this might actually increase the gap between the different populations. Because the moment your budget decreases, it means that you will target those people where you expect more criminality even more. Now, if your belief is already wrong, this might actually have very, very bad or counterintuitive consequences. So, but we will briefly talk about that, and we will talk about sanctions. Now, by sanctions here, I mean exactly the cost of having an unbalanced set. Again, we are taking that from a symmetric point of view, so you're not being punished for targeting one group or the other, you're just being punished for having an unbalanced set, which can go in either direction.
But this, part of this is what Amnon asked, or this is separate from that? Because if I have an unbalanced set, I have a decreasing marginal utility from search.
You have, so there are two things here. The one thing is the true criminality rate. The other thing is what you believe the criminality rate is. Now, when you solve your optimization problem, you work with your belief, which might be entirely incorrect. Now, if you overestimate the probability, this means that the point of balance where the marginal rates are equal will be much later. That's the problem, which is why a higher belief will basically cause that you oversearch that population.
You mentioned an assumption regarding budget cuts that the effect is differential. Why is that? Suppose you have fewer cuts, but they are behaving the same way.
So my statement with respect to budget cuts would be it's non-monotonic. If you have very, very small budgets, increasing the budget can actually increase racism. If you have large budgets and you decrease them, the same thing can happen. I will.
Why is that?
Let's take the simple example. Suppose you have a budget of 0. You discriminate nobody. Discrimination 0. Suppose you have a budget of 100%. You can check every single person. Well, you will do that. You discriminate nobody. But in between, these things will at some point go apart from one another. You will discriminate against one group, and as the budget increases, the gap will decrease again.
Alternatively, the budget affects the number of cups, but not the behavior of the individual cups. And then there's no effect in discrimination.
We make no assumption that the budget affects behavior. What we have here is a constraint optimization problem, and the budget is just that, just the constraint. It's just a sentence, exactly.
If you increase the budget, it could be that you come late.
זה לא חשוב.
You don't check it often.
לדקדק את המדפסת חשוב.
Okay, so when I talk, maybe I should be more clear what I mean by budget. What I mean by budget is the number of people you check. That's the budget. You check 1% or 10% of the population. That's the budget. This can go up or down. Of course, if you say you pay them better or worse, this can have different things. I'm just talking about how many people you can check in the street. But this was basically the discussion in the late 2010s whether this idea of stop and frisk should
So
be
this
abolished.
also goes to all kinds of regulations that people have proposed for how often can you frisk and search, for example.
Yeah, that goes precisely into that. So in 2010, well, I showed some of the data later, and you see that these numbers have changed tremendously in 2013. Alright, so I've already told you some about the findings. Now from a theoretical point, the equilibrium that I showed you always exists. It's not unique, simply because you could develop a zero belief over some time and then you will never search that, if you have sufficiently low budget that supports this corner. The interesting equilibria are of course those where you search everybody with some probability, where you do not have these zero beliefs. These equilibria are the nice equilibria. They unfortunately do not always exist, but if they exist, they're at least stable in the sense of if you play that game of search, belief update, you converge towards this.
If I have non-discriminating beliefs, that's an equilibrium or
No.
no?
Well, depends. It is an equilibrium if and only if criminality rates and race are uncorrelated. Then it is an equilibrium, if and only if that is true. Otherwise, you can never reach that point. Right, so
What is the target function? What do you like to maximize in this?
I get there. First key findings, then I will give you the model.
Suppose I start from non-discriminating and then I update according to the findings. Will I get the right result?
You will get to this well-ordered equilibrium. I mean, you will get it right in the sense that you're discriminating against those who are most criminal, objectively speaking, but you will totally overestimate how criminal they are and you will set them way too often.
Still over.
Oh yeah. I mean, this thing really puts you off track. Equilibrium here is bad. You're doing, when you're in equilibrium, you're totally wrong, but you're doing pretty much what we see in the data. Okay, right, so here, discrimination always goes hand in hand with overestimation of criminality rate. If you're discriminating against somebody, you're overestimating criminality rate. What can happen, interestingly, is that you're discriminating against the wrong group. So that there's a group which has a very low criminality rate, but you're still over-searching them and you never figure out that you're wrong. That can happen.
Why would that happen? I mean, will it happen all the time?
No. Okay, let me rephrase. There are such equilibria. I have a very strong suspicion that these equilibria are unstable, but I was not able to prove that yet. All the equilibria that we have found of that type are unstable.
In what sense unstable?
You change the belief or the behavior a bit and you will never come back. But in the sense of updating, optimizing, this is always the dynamic we're interested in. If you are in one of these weird equilibrium, you change your belief a little bit, you go off.
Just to be sure that I understand it correctly, the last sentence, discrimination always goes hand in hand with overestimation of criminality. Isn't it the definition of discrimination? That's what I thought.
Well,
this is like a statement. It goes always hand in hand.
What I mean here is...
What is the definition of discrimination, if not that?
You're searching that too often.
Too often, what does it mean?
Often
Isn't it
others.
this what you say by over...
Okay, good. Okay, let's be precise. When I say discrimination against one group, I mean that you're searching this group more often than another group.
this is your
This is
definition
my
of
definition
discrimination.
of discrimination, yes.
So this makes
And if you and you claim here, this is a statement that if one group is more searched than the other, it means that there is overestimation of the criminality rate. Why is that?
Of the group that you're discriminating against.
Yeah,
So in equilibrium,
because it might be that you estimate this group has more criminality rate, and that's why you are searching more in this group.
exactly. I mean, this is what happens in equilibrium. I believe that they are more criminal than the others
So why overestimation?
because there is an objectively true criminality rate, and my belief is way above that. Well, let's say there is a group I'm discriminating against them. 5% of them are criminal. In equilibrium, I will probably believe that 10 or 12% of them are criminal.
Okay, it's not totally clear to me, but I can hold it until I see the model. Okay.
So what I mean by overestimation here is my belief is higher than the actual number.
the third line from the bottom appears to say that if you could identify the bad guys by appearance, only they would be stopped. But referring to this as discrimination is somewhat, I don't know, debatable.
Okay, so there's something called statistical discrimination, right? That there's simply a group that is more criminal and targeting them more often. That is statistical discrimination. We are not the first to point that out. But what we are saying is that if you do that, let's say one group is 10%, one group is 11%. Okay, so I should target the 11% group more often. That's statistical discrimination. What I say is that in our equilibrium, even the true numbers are 10 and 11%, it will look like, or I will believe that the true numbers are 5% and 20%, and I will discriminate not slightly, because they're slightly more criminal, but I will search them like 3 times more often. That's the problem. So we are in a world where we have the kernel of truth, in the sense that we order them correctly, but our beliefs are basically expanded. Those who are searched too often, we totally overestimate how criminal they are. Those we are searching very seldomly, we totally underestimate their criminality. Which then, in equilibrium, causes the fact that we search the more criminal a lot more often than the others, even though the true difference is very small. That's the problem. And in particular, we cannot simply explain what happens here by statistical discrimination in a kind of reasonable way. So what I mean by that I will also show you.
Size of the groups does it mean better? The sizes of the groups.
You mean the total number?
No, yes, you're saying you will get 10% to 11, but you don't mention the size of the two groups.
it does matter for some results. Now in the data here, sizes are fairly comparable. I think the smallest group is 25, the largest 33%. This will not make trouble in the empirical part. Okay. Now, I've mentioned before, discrimination is non-monotonic in budget, meaning that if I increase or decrease the budget, it can be good for discrimination or bad, either way. But what is clear that if I'm sanctioned against having this broader variance across types, then I will be less discriminating, which is, well, kind of clear. I mean, for the optimization problem, it's clear, but it also holds an equilibrium. Maybe that's an interesting statement. Okay. Now, if we go into the dynamics, quotation mark here, our best reply dynamics would be, well, we develop a belief, we optimize, we develop new belief, we optimize, and so on. This dynamic converges, and if we start from an unbiased sample, we are converging towards an equilibrium that is well ordered, but still incorrect, at least if there is a correlation between race and behavior, which we call appearance. All right. So,
What does correct mean here?
correct order. I mean.
No. Is there are there correct numbers for searching any group?
No, when I was talking about a correct order, meaning
Okay.
that those who are searching most are actually those who are most criminal, and those who you believe are the most criminal. So this is what we mean by kernel of truth, that the order is preserved. All right, good. Now, very briefly, some literature. Now, statistical discrimination, I already mentioned, started with arrow. This has been applied to optical police search even more recently. Now, racial bias is also rather an old topic, mostly in social sciences. Now, one thing that we have to make clear here is that the decision to abide the law is exogenous. Right? It's not that, well, I will be searched more often, so it's more likely that I abide the law. So basically here, our individuals cannot help themselves. Either they're criminal or they're not. Which is a strong assumption, but at some point the model has to stop, and this is where we make the cut. Now, the idea of sampling and statistical inference heavily relies on these papers here by Justin, Fiedler et al., which introduced this naive intuitive statistician who makes the belief update in the way we do it in the model. I'll give you the details in a second. And then, of course, there's quite a lot of papers in the learning literature where you somehow do something wrong with the data you observe, or basically where you ignore your sample bias. And this is precisely what we're doing. We're ignoring the sample bias. Good. Let's go into the model. So, we have a population which is simply unit interval. These are the people we might stop and frisk. They have a conduct which is either good or bad, and they have an appearance which is their race in this context. So, conduct we cannot observe, appearance we can observe. There is, so the conduct and appearance together are the type, and there is some true distribution P over these types that we do not know. The marginal distribution of each appearance of each race is P of omega, and P superscript omega is a conditional probability of an omega type to be bad. So that's the probability that a white person or a black person, an omega person, is a criminal person.
This is a true probability.
That's a true probability. So we do not know that. Now, the designer or policeman has a belief, which we denote by Q, and what we assume is that at least with respect to how the population looks like, he's correct. He knows how many black people, white people, Hispanic people are in the population. That he knows. This is what we call consistency. And this person decides about the search rule, which basically maps each appearance omega into a probability of being searched or not. That's the thing that I try to optimize. How many percent of the black population, white population, Hispanic population do I want to search?
What's the marginal of Q on? Is there a marginal of Q, just like there is for P?
Yeah, but we don't need it. It might appear at some point, and then I will just call it P of B. This is just a notation that we will need. So far, so clear? Okay, good. Now, this is New York City. What you see here on the horizontal axis are search probabilities. On the vertical axis, you see success probabilities, the probability that the searched person has indeed been summoned or arrested following a search. And what we see, of course, is that if search probabilities are very low, the success probabilities are very high. So this here is 2%, so here we are in the area of 0.2% of the population being searched, and you see up to 40% of the search individuals actually were summoned afterwards because there was an outstanding warrant or they were carrying a gun which they were not supposed to, something like that.
It's not necessarily correlated. It's not necessarily that if you make less arrests, less searches, you succeed to locate the bad guys more oftenly. Maybe the budget is small for taking them to the station, you know? So you have a budget to take to the station, you have a budget to make searches, and now you collect only the worst of the worst people you take to the station. It might be, I don't know.
It might be. What we see in the data is for every single search that has been conducted, what happened to that person afterwards. What was the suspicion, what happened. So basically a police person would have to write there all clear to let them leave again. So I'm not sure whether that is true. The other thing is, when I say a successful search, I do not mean that they are arrested on the spot. It might also be that they have been summoned to court. So, but they'll leave immediately. So there would not be any budget issue here.
Okay.
So basically hand them a piece of paper, they appear in court in 4 weeks.
All there is a race.
So we have 4 races, white, black, Hispanic, others. Now, whites are very hard to see. Basically,
What is the point there?
the point is 1 year, 1 race, the search probability in that year for that race, and the success probability of the search. And what you see that these guys here are all black people, or black dogs, right? So the black population has been searched up to 20%. 20% of all black people in New York have been searched within a year, which is a huge number. The white population is mainly in this area, as is others, and the Hispanics are mostly in. I will show you that picture later again, where it is separated into the different groups. Then this will be more clear. But the point I want to make here is that the more you search, the less likely it is that a search leads to a summon or an arrest. Which is the part we ignored in our first version of the paper and developed here. Now, if we have that, we have to define the kind of productivity function of searches.
So the target is to maximize the rate of, what is the target?
Yeah, we get there. But let me talk about productivity first. I will give you the objective function in 1 or 2 slides. So, what we have here is a productivity function that depends on search probabilities and criminality rates. So on pi and on q gives you a number between 0 and 1. This is what I expect to find. And I will give you a lot of assumptions later on, but for now, for the general part, what I want is that this thing is linear in criminality rates. If you have twice as many criminals, you find twice as many people. I want that this concave in pi, meaning decreasing marginal return, which ensures that we have this shape. And we want that this function is independent of omega. And so no matter what group I'm searching, it's always the same function. So it only depends on the search probabilities and the criminality rates, but on nothing else.
In this assumption from your graph, we can say that liability is different for different groups. Do you have data about the race of the police officers?
I think we do not have that. We only have.
Because the main objection probably would be that people who are white are able to recognize white when they're criminals. They're unable to do that for blacks.
But that we do not have. Okay.
Why would it be linear?
Because it makes the model tractable. So that
The best answer. No more questions. I rest my case.
yeah, sorry.
But also,
I think the concavity in pi is quite clear. The linearity in q we can discuss. To be honest, my biggest problem I have with the independence of omega.
why is that?
Well, let's say I search a person and this person has conducted a minor infringement. Then basically I might behave differently depending on whether the person is white or black.
But then you condition on criminality of that because Q omega is an argument.
Q omega is the argument, yes. But suppose I have this person in front of me and I find, let's say, a joint in their backpack. What do? If my decision depends on whether this person is white or black, then I'm violating this here. That's the problem. So everything here we make under the assumption that the actual behavior, once the person is searched, that will lead to an arrest or something, is identical across appearances, and I very much doubt that it is.
So you have two actions to take as an authority. One of them which one to search, and the other one what to do with the new.
Exactly.
So two actions. Or
We
three
ignore-
or four.
We ignore the second one. Here we only say you're searching, and that's it.
Oh.
And you decide for all on a very standardized base whether or not to arrest that person. And this is entirely dependent. So basically we exclude all forms of racism after search. Okay. Now what you see in this picture here is the success rate, which is basically our productivity divided by the search probability. As long as rho is concave in pi, this thing will decrease. In about 20 minutes, I will give you a more specific form about rho, but for now, let's just say it's linear and q concave in pi. Okay. Now we come to the objectives. Now, we want to optimize this search. Now, the average search probability is basically all the searches weighted by our population. That's clear. Now, this is basically what is given to us by our budget. So we can search up to that many people. Now, what is our expected productivity? Well, if we have a search group pi and a belief q, what we do is we have a weighted average of the productivity of the different groups. So this is something that is good. We would like to get this thing large. That's part of the objective. The other part of the objective is we do not want to appear too racist, and we measure that by variance. So what we do here is we measure the quadratic difference from the actual search probability to the average search probability, we weigh that thing and we normalize by the average. It's basically a variance. These are the two ingredients for our objective function. What we want to do is we want to maximize utility function that depends only on E and V, that is increasing in E, decreasing in V. And we are maximizing subject to this high bar here not being too large because there's a budget constraint. Later on, we will make a very, very simple assumption, namely that the utility is E minus VV, where V is just some positive number. So, then this is the problem. Maximize utility subject to probabilities between 0 and 1, and average probability not being larger than some exogenous budget k between 0 and 1. Now, this problem has a solution. And this solution is unique because it's a strictly quasi-concave problem, or strictly quasi-concave function on a linear constraint, so there's no problem there. And this thing is well ordered in the sense that if I believe a type omega to be more trivial than a type omega prime, I will search them more often. That's well ordered.
If I didn't care about variance, it could be that I will search only one group.
Yeah, could be. I mean, it still need not be the case because it's marginal rates that we are trying to do, right? So depending on how concave functions are. But even with the variance, it could be that you're only searching.
I see.
It reminds the mean variance portfolio selection problem, no? Might be. You
I don't know.
don't make the connection.
Okay, good. Now, if our function is sufficiently concave, meaning if the marginal rate decreases sufficiently fast, and our budget is sufficiently large, we have an interior solution. Then we will search with some positive probability. Okay,
What is K?
K is budget. This is just the highest average probability budget.
And rho is?
Rho is this productivity function. If I mean sufficiently concave, I mean with respect to pi, which is probability. In the beginning, you find quite a lot of people, and then over time, the margin rate decreases.
So rho is a function of two volumes?
Yes, of pi and of q, but it's linear in q. Okay, so that's the objective. Now, let's talk about the naive intuitive statistician. So what you see here is a protest march in 2012. Now, this gentleman here is Al Sharpton, who is an activist for civil rights. And between 2010 and 2012, they were marching to abandon this stop and frisk clause. Now here I give you data from 2010. On the left-hand side, you have the population of New York City. On the right-hand side, you see arrests and summons that have been made in the context of stop and frisk. And what you can see here is that of these 82,000 arrests that were made, 42,000 were actually black people.
What did they search for?
He looks suspicious. Open
Okay.
the backpack.
And then what? They search me and find what? A gun, a
A
knife?
gun, a joint, a knife, an outstanding parking ticket.
What did it?
An outstanding parking ticket.
Ah.
You have not paid your fines. Well, whatever. They will check your identity, they see what's going on, and if anything was wrong, you get a summon or an arrest. Okay. So here is what the naive intuitive statistician is doing. Or well, this is what you're doing. You're saying me, well, from these data, the probability of a black person being criminal cannot be assessed because I'm not telling you how many black people actually have been searched. It's just missing data. tell you what the sample is, I just give you these things. Now the naive intuitive statistician doesn't care about that problem. As well, simple. There are 82,000 criminals, 42 of them are black. So the conditional probability of a criminal person being black is more than 50%. And now we can compute the conditional probability of a criminal person being black by its rule, and we get about 2%. So basically what this person is doing, they're dividing that number by that number. Right? And for black people, we see that's more than 2%, whereas for white people, it's only 0.27%, which means that the black population is way more criminal than the white population. That's a naive intuitive statistician. Which of course is nonsense. Because if I give you the middle column, you see these are the actual searches. And now we can make some computations, and what we actually see is search probabilities for white are 2%, for black it's 17%. And well, the question, can this be due to simple statistical discrimination as we discussed before? People are more criminal. Does it justify that we search them more than 80 times as often? Now, what we could do is we simply compute, well, what's the probability that one of the search person is actually criminal, and for the black person we see that's 13.4%. That's a success rate in 2010 for black people. We can do that for every type, of course, and what we see is it's almost the same numbers. In particular, it's not even the highest number for the black population. So, which means that statistical discrimination alone is not sufficient. There is something else going on here. And our claim is it's the incorrect beliefs that come from the intuitive statistician.
If they're the same numbers and they care only about the expectation or the variance, then statistical discrimination would be a good explanation. Right? If I only care about the expectation, I would like the success rate to be the same across all groups, no?
Okay. Yes, but here in this area, the numbers are the same. There's no difference between the different groups. That's the problem. So what we have here is very sharp decrease here, but once you reach a certain thresholds, the numbers are just constant. And we are, in 2010, we are in an area where we're basically comparing somebody here with somebody here. Okay? So, I'm not sure, I'm not convinced, because if you would search with the black person with the probability here, you would still find the same. You would still have the same success rate. And so the success rate just doesn't change that much anymore in these high ranges.
Evidence, like there are years in which black person are only searched 2% of the time. There is data like this.
I will show you that later. It changed in 2013. In 2013, the stop and frisk policy was abolished, and then all this is basically when we moved into this area. So until 2013, we're basically here.
When you talk about the probability of a black person being bad, is that conditional on being searched?
No, not yet.
So how do you know?
You do not?
How did you derive this figure?
I do not derive anything here.
You had a specific number telling us what is the probability of a black person being bad.
Yes, a black person to be criminal after a frisk.
After frisk?
After frisk. So that's for this sample. I'm not saying anything about the population because...
so if the numbers are the same across different ethnic groups, this means there's no discrimination. Yeah?
This would be if you would not have this constant area where the success rate doesn't change anymore. And again, what what you also find here, if you put the numbers, I should have put them on the slide. I think for the Hispanics, actually, the number is about 14%, instead of 13.4%. But Hispanics have a much lower probability of being searched.
Again, if the numbers are the same, if you are making if you are making a mistake, you are arresting an innocent person, if the probability of that is the same across all ethnic groups, doesn't that mean that there is no discrimination at all?
This would be the case if you still had a decreasing margin of return, then yes. But if your marginal rate of return is constant, as it is after some point, then it doesn't, because you could have searched fewer of one group and more of the other and still have gotten exactly the same numbers. That's the point. The other point is, the numbers are not exactly the same. So the counterexample would be Hispanic people who have a sample probability of being criminal of more than 14%, 14.2%, but who are searched with probability of, I do not know, they're searched half as often, but they're a larger group, much lower probability, higher success rate. So you're discriminating against black people compared to Hispanic people for some reason. Even if you do not assume that the marginal success rate is constant. Okay, now, so let me try to formalize this thinking of the intuitive statistician. Now, this here is the sample probability of finding a criminal. Right? We simply weight the successes we had in our sample. Now, the appearance omega condition of being criminal is basically the success rate in the omega group divided by that number. That's this here. Now we say that the belief is now admissible if my success rate, given the actual sample, and my belief Q is the same thing as I would have had in the true criminality rate had I conducted my search in a balanced way. This here is the success rate that I observe, and I try to explain it by Q. Q is the variable here. This is what I would have gotten if my sample would have been correct with the true criminality rate P that I know. And now it kicks in that these two things are linear in P and Q, because it gives you then a very, very simple relation, namely Q is simply P scaled up by search probability for omega divided by average search probability. This also means that you have to be...
It's like a replicated dynamics, right? Essentially.
I don't know. I haven't made the connection. Okay, maybe it does. And you see here, you might get into trouble if the pi omega is too large, so that this might actually blow up and become more than 1. Then, of course, the whole thing crashes. So we have to talk briefly about existence.
Can you come back to the slide? I'm not sure I understand. So this means that if I search some group twice as often, admissible belief will assign them, will imply that they are twice as often as criminals as they are truly are.
This is what you will believe afterwards, yes.
So what? So rho is true. The productivity function is true, or it's only my belief? There is a true productivity function out there.
Well, the true productivity function would be the productivity of your search probability with the true probability P. But this one we do not know.
So let's say I search and everyone has 10% of being arrested, but I search the black 3 times more often. Then I only believe that if I were searching them 3 times less often, like other people, like white people, it will remain the same. This is my belief. I don't understand that the probability of being arrested is decreasing with the self probability. This is what I don't understand correctly.
Not quite sure. let's say you have searched them 3 times more often. This is what we have on the left side. So pi omega is 3 times the average. So pi omega is 3 times the pi bar. So this here is what you would have found if you have searched, if you have had a non-biased sample. And you ignore that your sample was biased. That's the point. You ignore that you do not know that, you are unaware of that, and what you do is you simply divide by your search probability. But this is where the problem arises. And this is the correct thing on the right-hand side. This is what you observe. And you use Q to explain it. So what must be your question is, what is the criminality rate that would explain what I see here, under the implicit assumption that my sample was unbiased, even though it wasn't. This is what you do.
Unbiased in the sense of the same search probability for all groups?
Yeah. But the same search probability for all groups means that your sample has the same composition as the overall population. Another example. When I was in high school, we were a class of 30 people or something like that, and there were always, for every test, about 5 people who got an A. 4 of them were girls. Now you could think that girls are much smarter than boys, until I tell you that out of these 30 people, we are only 4 boys. So that's the kind of mistake we're talking about here. Okay.
This would be equivalent to hiding the column of the cells as we did before.
Exactly. This means exactly you hide the sample. Okay. So now you have a search rule if and only if this inequality holds. If the belief exists, it's unique. I mean, I gave you the formula. Of course, it's unique. And you overestimate criminality. Your belief is higher than the actual probability if and only if you're doing over-searching that truth. Which is clear because pi omega or pi bar is exactly your scaling factor. Now, a sufficient condition for this here to be true is that the true criminality rate is smaller than the share of the population. Now, share of the population in our data set are about 25%. So unless you believe that 25% of all New York people are criminal, we're safe. Okay, now, good. So, now we come to equilibrium. Now, we say a pair of a belief and a search rule is in equilibrium if your belief is admissible at pi, so it comes exactly from pi and what you find, and pi solves the design optimization problem at Q. In this problem, you will just continue in behaving that way because you will never figure out that you are actually making a mistake. It's self-confirming in this very abstruse sense. Okay, so what about existence? If we have this condition here, which was sufficient in order to get us beliefs, then there is an equilibrium.
Omega is a finite set?
Omega is a finite set, yes. In this equilibrium, we have that Q omega is at least P omega if and only if I'm over searching. Right? This is basically the previous slide. And here's a nice thing. Q omega is larger than Q omega prime if and only if pi omega is larger than pi omega prime. Now, if you have paid a lot of attention, you will have seen that for the optimization problem, I didn't have an if and only if here, but only an if then. Now, in equilibrium, it becomes an if and only if, because in the pure optimization problem, the only case where this goes wrong is if we have a corner solution. But if you have a corner solution in equilibrium, the belief is 0. Which is why we have an if and only condition. So, what do we have? We have overestimation, meaning over searching, and we have the beliefs are ordered according to search probabilities. What we do not have is that search probabilities are ordered according to true criminality rates P. That we do not have. And there are counterexamples.
Can you please remind me what is the inequality in the first,
This one?
no, the P omega less than P omega, what does that mean? First line.
This is the true criminality rate. This is the share of the population of race omega. In our sample, I think the smallest population group is 25%. So as long as in this group, not 25% of the population is criminal, we're safe. Fine. Good. And here's the corollary. You can find an equilibrium with correct beliefs if and only if the true criminality rates are equal across races. That's the only way. Alright. Good. So, let's simplify the problem. Let's now talk about the linear objective function. So we have a budget K, we have sanctions for being discriminating, which is B. And now here, I'll give you some numbers. Actually, I should also give you the row, but never mind, I'll see it later. We have two types. Both appear with 50% probability. One type is more criminal than the other, 10%, 5%. B is 1. And what we do is, we vary K and see where the equilibrium appears. Now, what happens is that if you have a sufficiently large budget, you find equilibrium is here on this curve. Now, what is that curve? Well, on this axis you have K, on this axis you have search probability for type 1, which means that once we are above the 45-degree line, we're searching this type, the one type more often, which this is the 55-degree line. So in all these equilibria here, the search probabilities are ordered correctly. We are searching the more criminal type more often than the less criminal type. So there's discrimination, but we have cut off through. Here is also equilibrium, but we are below the 45-degree line, which means in this area here, we are actually searching the less criminal type more often than the criminal type, which is strange, but it's still equilibrium. Now, why does the good equilibrium disappear here? Because we would get a belief that is larger than 1. We were talking about this point.
But what is the production probability? The production function?
It's exponentially decreasing in search probabilities. I will give you the precise formula in a few minutes.
And the equilibrium is unique? Whatever you show here is the unique equilibrium?
No. There are more equilibrium. Also, give me a second. You always have the problem that zero beliefs give you an equilibrium where you only search one type. Or can. Do not always, but can. So, good. So these two lines are the interior equilibria. These are the equilibria we're actually searching both types. But there are others. Now, okay. Let's maybe go there. Now here's the dynamic that I've been talking about a lot, right? You update your belief, you make a search, you update your belief, and so on. Now, this is the dynamic. That you're converging towards these lines. So these are the nice and good and stable equilibria. In this area here, you're actually increasing until you arrive at this corner line here, where you assign your whole search probability to the more criminal type. Here, in this area, you're decreasing where you search only the less criminal type, which means that this green line here gives you your stable equilibrium. stable in the sense that if you just change your belief a little bit, you will converge back. It's a very weird shape, but it also gives you an idea of why we're doing it in a 2x2 case and not very successful, rather more general results.
It depends on if I know PW correctly, how would the curve look like? I have the same fund, the same goal, but I know PW, I'm good statistician, the economy, etc.
If you knew PW, well, then you would not have that dynamic, of course, because you will not develop a belief. Let me come back to that later. I will give you a comparison in the data analysis later, where I show you what our model predicts and what would happen if you actually do the P. Alright. So in this 2x2 case, the best response dynamics converge. And if we start with a balanced set, or balanced search rule, we always converge to the correctly ordered equilibrium. They're always going up. Okay. So now let's talk about what we do with our productivity function for our data. Now here's a micro foundation. What we want to do is that we want to ensure that our decision maker is better than random, so they know at least a bit what they're doing. We want to make sure that if they do not search, they do not find. That's clear. We want to have homogeneity in criminality rates. Well, that one we had before. We want that some criminals are actually detected by chance, in the sense of I cannot easily identify everybody. Right? Sometimes it's just random. And assumption 5, those who I can easily identify, they're decreasing in numbers.
Can I ask something on the previous slide? So you said your last sentence here was that it always converges to the right.
Order.
So it's like you finish the story, you should start your recommendation, let's say. You start with the same rate and you converge it to the same rate. That's what you claim?
What I claim is that if you have an intuitive statistician, even if they start by searching everybody equally likely, they will end up here in equilibrium where they discriminate.
In equilibrium, which what?
They will end up in an equilibrium where they discriminate against one group.
They discriminate against one group.
Yeah.
But not with the same,
Well,
their perception about the right rate will be correct or not?
No. They're still over-searching the more criminal.
Oversearch.
I mean, what you can see here maybe is, in this case, as the budget increases, this number somehow gets closer to the 45%, which is clear. If you have a budget of 1, you simply search everybody.
This depends on the budget. I see.
But basically, the discrimination part is that distance here between the green line and the 45-degree line.
So there is something that I missed. Maybe I just didn't focus. So they update their belief after they start, and they converge, and not always in equilibrium that you define. They converge not to the right rate, right?
Exactly. In equilibrium, they always have an incorrect belief.
Always.
Always. Well, generically speaking, always, unless the criminality rates are independent of types or of races. Then the equilibrium would be correct. Otherwise, they always converge to equilibrium with incorrect beliefs.
Even if they start with the right belief?
Yeah. I mean, even if they start with, no matter where they start, I mean, if you're in this, no matter where you are, you always converge to these guys, except for this very little part here, which is strange, but you always converge to a point where you overestimate criminality of some people. So it's sad. But
Okay, no, I feel like I missed the main part. I don't know the main idea, but okay, you can continue.
So our point is if you are in equilibrium, you're wrong. Okay, so, good. These are our 5 assumptions. Let's make them a bit more. Oh, okay, good. Sorry, I screwed up the order of my slides. We'll come back to that. These are the data. So we have population data from census, and we have search data from the New York Police Department, who were court ordered to publish them. So they're available online. You can search, or you can find every single search that has been conducted in New York City between 2003 and 2024, I think, by now. So now let's go back here, and let's make that mathematical. Now, better than random means we want to be better than pi times q. And this would be if you just conduct random searches. Now, if we do not search, we want to have 0 findings. Also, not that good. Homogeneity we already had. Basically means we're interested in a function that only depends by pi and multiplied with q. Now assumptions 4 and 5 are a little bit more tricky. Some criminals are detected by chance. What I mean is that there's some alpha between 0 and 1 and a map rho D such that rho takes a form where we have a part here which is purely random and a part here which actually has a decreasing marginal rate. This is random. These are the criminals that are easily identified. And what we want to have is that this part here, these easily identifiable criminals, they are decreasing exponentially. The probability that you find one of them is proportional to the number that still are in the pool. And if you do all that, you get a function that has the following form. Here's the criminality rate, here's the alpha part, right? These are the highly criminals, which is basically 1 minus search probability to the gamma, and here you have the random part. We have an exponential decrease here, and we have the marginal rate is exponentially decreasing, and here we have a little part. This is the function that we use in our data analysis. Because now we basically have 2 parameters in the alpha and gamma.
Between that gamma and the other gamma here?
This gamma here is that gamma here. This.
Oh, so it's gamma of QW.
No, here it is only gamma because it has to be a constant.
It has to be constant.
Because otherwise this part here would not be homogeneous in Q anymore.
Yeah.
So here we just assume that it is a gamma of Q, but together with assumption 3, it's constant. So that's the function. Okay. So we fitted our data. We'll tell you later how we did that. And these are basically it's the same picture from the beginning, but now with functions. Now you see they are not perfectly going through the dots because it is not exactly what we fitted yet. But what you see here is all the white people are on that. That's the line for white people, and this is where the search probability for white people stops. But about 2%. There were no year where we had more than 2% of white people being searched. For others, went up to 4%, for Hispanics, almost 10%, and for the black population, up to 20%. So, and the parameters that we found are a very, very small alpha, which gives a very, very small exponential part and very, very large gamma, which means that this part is very steep. And in particular, after some point, it's almost constant. Now here are again the 4 groups separated.
So this a period of 17 years, the criminality rate is similar. So if some points later year or criminality is substantially lower, right?
We make the implicit, or we make in the fit we make the assumption that
there
it's
was
constant.
a substantial decrease in crime, right, in these 2 decades or not? Or it was earlier?
I think this was earlier. I mean, stop and
It's
frisk.
roughly constant in this.
Stop and frisk was kind of a response to that, right? But our assumption is that it was constant over time. But basically, we do not know what else to take as an index here. So how did we fit the data? Well, we did a grid search for the two parameters alpha and gamma of this productivity function, and this parameter b that told you how averse you are against seeming discriminating. This was the parameter for the variance. Now for any alpha, beta, gamma, we were looking for true criminality rates that best explained the previous pictures. Now this is easily done because it's only one parameter. You can basically write that down. It's explicit. And what we did then with the criminality rates and these three parameters is we find the equilibrium. Basically, we start with a balanced search and then do our dynamics until we are in equilibrium. And this equilibrium search rates we then compare with the search rates we find in the data. And here we are minimizing the sum of squared relative errors, and this basically gives us our alpha, b, gamma, and the corresponding p. And this is how it looks like. And so here you have the years, here you have the black population and their search probabilities. Now the dots is empirical, the dotted line is our estimate. Here you have Hispanics and the empirics. Now a problem that we have in this data is at the bottom. We have others are triangles and whites are circles, but our estimates are switched.
From a methodological point of view, what does the fit mean? I mean, you have 3 degrees of freedom, you search all possible values, and you get something that looks like pretty close. But is there any sense in which the model can be certainly validated by this statistically or otherwise?
To be honest, I'm not a econometrician, but my feeling is it's too few data points. And at the moment, what we are doing is basically take all the data and try to break it down not on annual basis, but on monthly basis, so that we get more power here. That's one thing. The other thing is, which you might observe, that there's something happening here.
But there's a drop in the number of search,
Yes.
which you take into account in your theoretical model. So that's not surprising that when the true numbers dip, also your predictions dip.
Yes, but what I wanted to point out is that in 2013 something happened in New York City. On March 5th, the chief of police issued an order to all police people that they basically had to report why they were conducting a search. And now suddenly the cost of being racist was much higher. You had to justify yourself. Which is why we assume that here there's a break. Which is also one reason why we try to break it up on a monthly basis. Now, our first results, I do not have them on slides yet. In our first estimate, what we basically did, we split the data into one group till 13 and, until 12, and then one 13 to 20, and computed that separately. And then the order is actually correct. That works. But we still haven't done it on the monthly basis because for that we need to re-aggregate the data in a different way, and that's a bit sad. But so this is basically what happens if we allow for our model. Now I could say, well, so many degrees of freedom, so few data, not surprising, I'm with you on that. But we could do the same thing under the assumption that our decision maker actually knows the true the true discrimination, the true criminality rate. We could do exactly the same exercise, and what we do is we get these pictures. And as you can see, they are very, very different, right? So they're much, much closer together. And except for this one group, would say they basically fail everywhere. So this is what I meant when I said I think that our model predicts these data much, much better and should be accounted for in any decision with respect to how any sort of risk policy is being implemented.
So first it's quite impressive, but second you model has additional degrees of freedom, right? This is much less degrees of freedom, the model when you know PW.
No, it's the same numbers of freedom. I mean, here we still have to estimate PW. We still estimate PW in this graph the same way we estimate it here.
Just assume that in the model, they know.
Yes. I mean, the QW and the PW, they are related. This doesn't give you any degree of freedom. If you know the PW and the PIW, you also know the QW.
So for example, there could be empirical data where your model would be significantly outperformed by a model in which you know PW?
Could be, yes. Could be. And it's the same degrees of freedom, we're just using a different function. It's the same degrees of freedom. This suggests that the decision maker does not know the true analysis and doesn't care. They have their estimate, which comes from by a sample, they're unaware of their mistake, and there's no reason. Okay, good. That's basically it. So we have this equilibrium with the intuitive statistician who always discriminates, generically speaking. They always consider groups more criminal than they are, if and only if they're discriminating against them. They're unable to detect a mistake. We are in equilibrium, equilibria are stable. And there's some equilibria where we violate the kernel of truth in the sense that we discriminate against the wrong group. Although we are quite certain that these equilibria will not be stable, we are not able to prove that yet. Now, my claim is, it explains data surprisingly well, but we have to do some follow-up work on that. But for sure, I think this has to be acknowledged when we talk about whether or not we should define the police, introduce sanctions, etc., etc. Because the behavior of this equilibrium is just very different from an equilibrium where you actually know what you're doing.
Defining the police, there are issues with the budget, right? What is our budget? But there is another issue, there is the real budget. It could be that the real budget of the police will be decreased, and your budget will increase. So for example, I remove all my friends who cause me to stop working and go eat donuts, for example.
But then I would decrease budget.
Yeah, you will decrease the budget of the
Oh,
actual
okay.
police.
Okay.
But your budget, what we call budget, will increase. Yeah, there will be more searches.
No, there will be more searches if everybody's go eating donuts.
No, if they're not. So if I remove these guys, who cause me not to work,
Okay.
then I go and work, and then
Right. Yeah. Yeah, but let's not talk about that. Okay, good. So, I mean, one thing that should be done, in my opinion, is give less room to incorrect beliefs, right? So, in particular, publishing statistical analysis of the entire report. What the NYPD has been doing until they were court ordered to release the data was basically proving that they were not discriminating. There's the New York Civil Liberties Union who got the data and basically went the other way around and only looked at all the innocents who have been searched and said most of them are black people, so you are discriminating. So depending on whether you look on those who were arrested and summoned or those who were released, you get two very different stories. But and both stories are used on both sides of it. discussion here, but for some reason the honest discussion that actually looks into both sides of the data hasn't been done for some reason, at least not in this political sphere. All right. Now, how do we reduce belief in search bias? Well, of course, B is the important part, as we can, or as we think we can see from the data, is this point of actually making police officers accountable for their searches, in the sense that they have reported, changed B. So what we find is that in these later years, the B is much higher.
May I ask something? So, what is the source of their rationality mistake, violation? I mean, is it correct to describe it as if they don't know the function of probability of
No.
finding the criminal after given a search, or what?
The mistake is sample bias. They see how many criminals they have put in prison at the end of the day, and they ignore who they have searched before. So
It's very easy to fix it, right?
yes. I mean, if you look
Just
at
to explain that you don't have to.
yeah, if you look.
So they don't know the function. This is the mistake, right?
No, they know the function. They just do not know who they have searched.
Yeah, right. It's the same, no? They don't know the connection between the rate of searching and how to compute the rate of criminals among population given the rate of search.
Exactly.
They don't know the function.
They're incapable of a proper Bayesian update.
Yeah.
They're incapable in the sense of they have a sample bias.
But my question is this: if they knew it, it might be that they should search in higher rate in the population with higher rate of criminals, right?
Yes, I mean you would still have discrimination, but a much smaller degree. I mean this is
No, I mean more than the probability of criminals in the population. Let's say one population 10%, 1% and the other 2%. They might increase the rate of search much more than double than in the first population, even if they were rational, right?
no.
So this is
So this is what they would do if they were rational. This is what they do if they update
now I
according
see.
to our model.
now I understand what you said before. Okay.
So this
So it's
shows
not
that so if they were rational, they would be discriminating much less. But
This is because you took into your target the element of variation.
Yeah.
But if the target was only minimize the criminals out there in the streets, they might want to take much higher power. So it's not clear whether it's
well,
what is the reason. I mean,
okay.
you can explain the data by rationality, but other target function.
If B is 0, so if we ignore variance, the fit would be worse, for sure, but it would still be blown up compared to that one.
Okay.
This does not depend on B. This also holds true if B was 0. And so you would
Maybe they want
still
to
have
take
always-
B negative to punish the population. No,
But actually, we were thinking about taking B negative as an idea of accounting for an appetite for racism, taste for racism. So
It's
the
the
problem is that the entire problem is not it's not a complex problem anymore. So then you have corner solutions. So then you need a different model. So our simple idea was to allow for negative B's, but if you do that,
Yeah, this is racist.
Okay. Right. Now
Dominik, we're out of time.
okay. That's my last slide.
No, I'm not stopping you, I'm just telling you.
Yeah. I mean,
Just knowledge.
one reason why I put this on the slide here is that in Germany we have an ongoing discussion whether we should investigate police racism, and typically the answer from politicians is no, we don't want to do that, because if we do that it would send the signal that all policemen, all these people are racist, which is very valid excuse, but so far we do not have this data in Germany, unfortunately. Okay, so thank you. And this is a QR code to the previous version of the paper, which did not have this decreasing margin return.